Thank you, Stefano. Okay, so let's first of all let's start me introduce myself so that we know a little bit each other. So I teach complex dynamical systems and control theory. I come from the University of Naples Federico II, which is in the south of Italy. You can see a picture of the Gulf. Here you have the famous or infamous Vesuvius. So that's the goal. That's the building of the university. The university is the oldest public university in the world. It has 800 years. We celebrated 800 years old last year. And so what? No, the public university. Public. So funded by the state, let's say, not by the Pope or the church. And so my current interest in research regards, of course, control of higher order interactions. In terms of application, I'm mostly focusing on the dynamics of human migrations and early warning signals in psychopathologies. Okay, so what are the activities that we do in our research group? So we focus on several applications. Let me mention some. So one is human motor coordination. So we study how humans coordinate the emotion where they perform group interactions. So this is very relevant, for instance, for rehabilitation. So when there are several, for instance, when you have, for people that had a stroke, they need to rehabilitate and to start interacting their motor interaction together again. So you can use virtual assistants, virtual players that can help to improve their condition, basically. Another application is related to human migrations. For instance, here you can see a simulation of the migrations that will be in the districts in Bangladesh. So Bangladesh is a low-lying country, so you will have that the coastal population will be flooded, the coastal areas will be flooded, and so the population will be forced to move by 2050. And so this you can make mathematical models that are basically compartmental models similar to the models that are used for disease spreading. You can use a compartmental model to understand how the population spreads will diffuse in the rest of the country. And so this is very useful in terms of getting ready, so getting prepared for what will happen next. Okay, other applications are related to opinion dynamics. We will see more about that later in this talk, and herding control. So when you have, for instance, a set of herders that need to contain targets in a given area. This is relevant, for instance, in search and rescue missions, where you have a group of targets that needs to be put in a safe region in a certain area. Okay, so what are all these applications have in common? That you have several, there are systems with several entities, individuals, compartments, agents. These entities are in interaction, and you have emerging behaviors taking place. Opinion consensus, target containment, motor synchronization, depending on the applications. So they can be looked at as network dynamical systems, where every node is a dynamical system. The interactions are captured by either graphs or hypergraphs, and you have a collective behavior that is emerging. Now, in this talk, we will, in this lecture, we will focus on a particular collective behavior that can arise in network systems, which is called consensus. We will explain what it is later. So, and we will see what will be the impact of higher order interaction in this, with respect to this collective behavior. And then we will introduce some. So in this context, we will see that the directionality is something that we cannot neglect. And so regarding what we were discussing earlier, so we need to define somehow directionality also in hypergraphs. So how do we do that? We will have to do it in a smart way, which is useful for our application. So there is not a unique way of doing it. It will depend very much on the applications. And in the lecture of today and in the lecture of tomorrow, we will see two ways of doing it, which will be most suitable for the application that we have in mind today and for the application that we will consider tomorrow. And then we will show how what we will have learned in this first part can be applied to explain how opinion dynamics changes when you have interaction of homophile, like-minded agents. Okay, so, well, the introduction will be quick because Stefano luckily make all the work for me, so you so you will be convinced that we need to go in several applications, we need to go beyond pairwise interactions. So now we are having basically a group interaction in this very moment. So we are talking all together. So you will make questions, and the result, the outcome of this lecture will be the outcome of a group interaction, which will be very different if we have a series of bilateral meetings with each other. Okay. And so the applications are vast. Stefano mentioned social contagion, the brain, and of course opinion dynamics. So let's focus now as an example on the case of opinion dynamics, and let's see how it has been tackled traditionally, so when only pairwise interaction were considered, and how do we need to approach them when instead we need to consider also group interactions. So the first dynamical model of opinion dynamics was comes from the 70s, from the work of de Groot, and in its continuous time formulation, the original formulation was in discrete time, but in its continuous time formulation can be written like this. So basically what do you do? So you associate a real number to the opinion. So you have a variable xi which represents the opinion of a node. This real number typically belongs to a given interval. So for instance, you have an interval between 0 and 1. Maybe 1 means that you are very convinced of voting yes to a referendum, 0 that you are very convinced of voting no, and then you have all the intermediate opinions. Okay, and then you have this variable sigma, which represents the strength of the interaction that are taking place between the nodes that interact with each other, so between neighboring nodes. Then you have the adjacency matrix that will describe the topology. So basically you will have the element Aij will be 1 if agents Ij are connected, they interact, or 0 otherwise. And then you will have this term which is related to the difference of opinion between node I and its neighbor. So as you can see, this term is a diffusion term which tends to equalize, to balance the opinion of every node. And so this has been used to explain how consensus among a group of agents emerge in the network. This was the simplest model of opinion dynamics. And what does it mean, consensus? In formal term, means that the opinion of all the nodes converge to a certain function key of the initial condition, and this function is a convex combination of the initial condition. So you have your initial opinions, and you will converge to a convex combination of these initial opinions. Okay. So now this, I would like to mention that this problem is not relevant only for consensus, only for opinion dynamics, but it's relevant in a wide range of applications. So in particular, this is very relevant in engineering, where you have, for instance, in one example is the rendezvous problem. You have a group of autonomous agents, a group of robots, maybe of ground robots, that needs to meet in a certain point in the space, and they have to agree on to which point they should meet, and they have to do it in a distributed fashion. Or you have a wireless sensor networks that is measuring the temperature in this room. So the sensors are identical, and you would like to they can communicate locally with each other, and they need to agree on the temperature of this room. So if all the sensors are identical, you would like that this function key was the... So you have a group of sensors that are measuring the temperature in this room. Let's say that the temperature in this room is 23 degrees Celsius. You put a bunch of sensors here measuring the temperature. So they all have the same accuracy. What would you like that then they start talking between each other in the neighboring sensors, and then they have to agree on what is the temperature of the room. What would be the temperature of the room? compared to, so the initial condition of the algorithm will be the temperature measured by the sensors. I don't know, let's say that one sensor measures 23.2, another 23, and the average, yeah. So more often than not, this function key is just the average. So in several applications, you are interested to that all the nodes converge onto the average of the initial conditions. This makes sense also from the point of view of social systems, because you would like to find to take a balanced decision which takes care of the input of everyone. Okay. Now, so the equation. So let's just go back to the equation. So as you can see, the equation in this equation, what will happen will be very much dependent on the topology. Okay, so we have this diffusion, but the way this diffusion will work will depend on the matrix, the adjacency matrix, and in particular, and so on the topology of the graph. So to understand precisely the role of the topology, we need to rewrite these systems in terms of another matrix which describes the topology of the graph. How many of you have heard about Laplacian matrices? Okay, not so many. So let's introduce it. So in general, a Laplacian matrix is a matrix which has non-negative elements on the diagonal, non-positive elements of diagonal, and importantly, it has zero row sum. Now, if you have any weighted directed graph, so there are the weights that Stefano was talking about. So in general, you have in a graph, the graph can be directed and can also be weighted. So you have the adjacency matrix A. So in this case, the element ij will be equal to the weight of the edge from I to j. And then you can define the Laplacian matrix associated to the graph. So instead of describing the graph through the adjacency matrix, equivalently you can describe it through the Laplacian matrix. And the Laplacian matrix and the adjacency matrix, of course, are related. And in particular, the off-diagonal elements are just the opposite of the elements of the adjacency matrix. And the diagonal elements are the sum of the elements on the corresponding row. Let's make an example just to clarify that. Let's make it for the undirected case just for simplicity, because so let's say we have these three nodes. So the adjacency matrix will be this one. Now it's very easy to obtain the Laplacian matrix, because in the off-diagonal elements you just need to change the sign of the adjacency matrix. So you get -1, 0, -1, and then you have -1, 0, -1. And then if you want to know the value of this element, you need to sum, so the element 1, 1, you need to sum the elements on the corresponding row of the adjacency matrix. So you have to sum A12 and A13, and you obtain 1. The same thing you need to do it for the element 22 and for the element 33. So as you can see, this matrix has non-negative elements on the diagonal. In particular, in this case, they are all positive. It has non-positive elements of diagonal, and if you sum the elements on each row, you can see that the row sum is equal to 0. Okay. Now, this matrix, just applying the definition, has two properties. The first property is that if you multiply L by a vector x, and then you take the ith element, you can write this as the sum for j that goes from 1 to n of aij xi minus xj. This reminds us very much of the right-hand side of the consensus dynamics that we wrote earlier. And then another interesting property is that when you compute when the quadratic form associated to matrix L, so you take a vector x, compute x transpose Lx, when the matrix, the Laplacian is symmetric, okay, so when basically aij is equal to aji, so it means that the graph is undirected, possibly weighted but still undirected, you will have that you can write this quadratic form as the sum over all the edges of aij, which by definition is a non-negative number, times the square of xi minus xj. This means that matrix L is positive semi-definite. So you know what is a positive semi-definite matrix? So when you consider the quadratic form associated to the matrix, this quadratic form will be always positive or zero for all possible values of x. Okay, so that's the meaning. Now, if we use the first property and compare it with the right-hand side of the consensus dynamics, we can see. So this was the right-hand side. So we have xj minus xi. Instead, in the ith element of the product Lx, we had xi minus xj. So we can write x dot, where x is just the vector that stacks all the states of each node, as minus sigma Lx. So it's a very compact way of writing it. And as you can see, now we can see that in this system, now we can see that everything that happens in this system is entirely dictated by the topology, because the dynamical matrix itself will be just the matrix that represents the topology with a minus in front and multiplied by a constant. So everything will depend exclusively on the topology. Instead, the type of systems that we'll talk about Stefano later, they will also have the individual dynamics in it. So they will always have another term, they will have an additional term here, which will not depend on the topology. So you will see an interaction between topology and individual dynamics. Here we will only see the effect of the topology by itself. So, to understand if we reach consensus or not, so if there is disagreement between the nodes, we need to characterize the properties of this matrix L. And from the properties of this matrix L, we will understand whether we get consensus or not. So first of all, we know that the matrix L will always have a zero eigenvalue with associated eigenvector given by a vector of all ones. So this is very straightforward to see, because if you multiply, so the fact that the matrix is zero row sum means that if you multiply L by a vector of ones, you can see it on this example, you will get a vector of zeros. If you compare this with the eigenvalue-eigenvector equation, you will see that 0 is an eigenvalue with associated eigenvector, the vector of ones. Okay? And then the second property comes from the Gershgorin disk theorem. I don't know if anybody, the circle theorem. So that tells you that if you take a matrix, its eigenvalues will be located in the area of the complex plane given by the union of n disks. The ith disk will be given by the diagonal element, the ith diagonal element, and the sum of the absolute value of all the off-diagonal elements of the ith row. So this might look complicated, but if you...
Let me just say that you are since now generalizing to the case of non-symmetric.
Yes.
If you have a symmetric matrix, by definition, all eigenvalues are real.
Yes.
You don't have imaginary values. But as he introduced the Laplacian, there is no need
Yes.
different way with respect to
Uh,
understand these
that's right.
sequencing things. The only important thing is the zero-row sum condition. So you can have a non-symmetric matrix. And non-symmetric matrices have complex eigenvalues.
And such eigenvalues will be confined to the right-hand plane, right-hand half of the complex plane. And this is because so this is the complex plane. If so, the disks will be centered in LII. So LII will be a non-negative number. Then the sum of the absolute value of the off-diagonal elements will be precisely equal to LII. So you can see here the absolute value of 1, absolute value of -1, and this comes from the zero-row sum property and from the fact that they are all the same sign or 0. So when you apply the absolute value, you don't mess up with this. And so the radius of the ith unit circle will be equal to LII. So, and if you take any other circle, LJJ for instance, it will have radius LJJ. And so you are guaranteed that the eigenvalue will be in the right half plane of the complex.
This is now my question. So now if you consider a non-symmetric Laplacian, are you guaranteed that you're always diagonalizable?
No? No. That's
What's the meaning here?
no, you are still guaranteed that the eigenvalues will be on the right half plane, but still, you might have multiple eigenvalues with multiplicity, with geometric and algebraic multiplicity that are different, and so still, we will talk about the fact. We will talk tomorrow about the fact that in general this matrix might not be diagonalizable. Yeah. Okay, and so as Stefano was saying, when the graph instead is undirected, of course all the eigenvalues are real because the Laplacian is symmetric, and so you can sort them in ascending order. You will have the smallest one, you will call it lambda 1, then the second smallest one, lambda 2, and so on. So now the thing is, interestingly, that still when the graph is undirected, lambda 2 of L will be positive if and only if the graph G is connected. So this is the reason also why it is also called it's called the Fiedler eigenvalue, but it's also called the algebraic connectivity because it tells you the connectivity of the network, that tells you that the network is connected. And so in an undirected graph, you also have another interesting property of the Laplacian. So the rank of the Laplacian will be n, which is the size of the Laplacian, minus the number of connected components. When instead the graph is in general weighted and directed, you still have an interesting properties of the rank of the Laplacian. So it will be n minus the number of sources of the condensation of graph G. What is the condensation of a graph? So you can always, if you have a directed graph, you can always condense it into its strongly connected components. So do you know? Well, I will tell you anyway. So a graph is strongly connected if there is a path from any node to any other node. Now, when a graph is not strongly connected, like this one, so for instance, here there is no path from node 2 to node 1, or from node 4 to node 1, or node 3 to node 1. Okay, so this is not strongly connected. But you can identify two strongly connected components in this graph. So one is this one. What is a strongly connected component? It's a subgraph of the original graph, which is strongly connected, of course, and is maximal in the sense that if we add another node to this subgraph, then it's not anymore strongly connected. Okay? So And the other obvious strongly connected component is this one, just node 1. So when you do the condensation, so if this is G, the condensation of G will be this graph here. So, well, this will be the two components of the condensation. Okay, so now if you count the number of sources of the condensation, you can, or better, you can count the number of sources of the condensation from the rank of the Laplacian, because the rank of the Laplacian will be n minus the number of sources of C. So in this example, the rank of the Laplacian will be n minus 1, because you have only one source. The source is a node with only outgoing connection, just by, it's quite obvious the name, but it's worth saying that it's a source node is a node with only outgoing connections. Okay, so now, with this, with some properties that we understood of the Laplacians and some definition that we got on the condensation, we can give the results on consensus. First of all, we can state and prove quite easily that consensus states are the only equilibria of this equation. So the only equilibria of this equation are of the type alpha times a vector of ones. Okay, so everybody with the same value. And so why is, and this is true when the graph G has a spanning tree. So the graph G having a spanning tree means that there exists a node from which you can, there is a path to every other node in the graph. Okay? So, if G has a spanning tree, so there is a node so that I can go everywhere else, so this means that the condensation of the graph has only one source. And so, we have the information on the rank of the Laplacian, which will be n minus 1. And this is enough, basically, because an equilibrium, to find the equilibrium, we need to set x dot to 0. So we need to find when minus sigma Lx is equal to 0. So basically, we need to find the kernel of L. So the kernel of L, well, of course, the vector of 1s belongs to the kernel of L, because L is zero-row sum. And also, the kernel of L will have dimension 1, since the rank of the Laplacian is n minus 1. So only vectors that are proportional to the vector of 1s will be equilibria for this system. Okay, so we have only consensus equilibria. And then we can give the following powerful theorem, which we will not prove. We will show just proof in a simple case, just to give you a taste of it. So when you have a graph whose associated Laplacian is a spanning tree, you have that the eigenvalue 1 is a simple eigenvalue of the Laplacian. All the other eigenvalues, since we are in the complex case, have positive real part. When you compute the limit for t that goes to infinity of the exponential of minus Lt, this converges to a constant matrix, which is equal to a vector of ones to a column vector, the product of a column vector of ones times a row vector W, where W is the left eigenvector of the Laplacian. And you know something about the components of the left eigenvector of the Laplacian. In particular, you will, and this is also it contains the topological information, because you have that, well, all the you can scale the eigenvectors so that all the elements are non-negative, and you have to scale it so that they sum to 1. But then, interestingly, the only positive one are the one corresponding to the nodes that can reach all the other nodes. So if node I can reach all the other nodes, then Wi will be positive. If yeah.
Sorry, in point 2, the exponential, you have exponential of
Yeah.
a matrix.
Yeah.
Which is a matrix. On the right-hand side, you have a matrix multiplied by a vector. And so
Oh, yeah. So you mean so you have this. So basically, the thing is that x will be equal to the exponential of minus sigma lt times x0. This will be the solution of the equation. So knowing the exponential of minus lt will be very useful to yeah.
But is the right-hand side a matrix?
It's a matrix. It's a matrix because this is a column vector and this is a row vector. Yeah. So, yeah. And so using basically this result, so you can compute then the limit for t that goes to infinity of xt. And so what you get is that you will have consensus, and consensus will be on a convex combination of the initial conditions given by the left eigenvector associated to the Laplacian. And so the only node that will contribute to the consensus value, so whose initial condition will be relevant for the consensus value, will be the one that can reach all the other nodes in the graph. Okay? So in this example, the only node that will contribute to the consensus value will be node 1. So everybody will converge onto the value, onto the initial condition of node 1. Okay? So this is a quite powerful result. But we are more egalitarian, so we are interested in average consensus. We don't want everybody to follow this guy. And so we are interested in average consensus. And so you have average consensus when the graph G is weight balanced, in the sense that the in degree and the out degree of every node is the same. Okay, when this happens, consensus will be on the average of the initial conditions. This happens because the Laplacian becomes also zero column sum, and so also the left eigenvector becomes a vector of ones. Questions on this part? Okay, if not, let me just show you the proof in a very simple case. So the simple case is when the graph is undirected and connected. So everything is, so all the eigenvalues are real. And we can find an orthonormal basis made of the eigenvector of the matrix. So this means that we can write the state of the system, so the stack vector with all the opinions of the nodes, as in this new base. So y1, y2, yn will be the coordinates in this new base given by the orthonormal eigenvectors. And so now if you can just with simple steps, so we can notice that pre-multiplying by vi transpose, we get the relationship, we get that the ith component will be vi transpose xt because the eigenvalues, the eigenvector are orthogonal. Then if we derive yi, we get the yi dot is equal to vi transpose x dot. We know the expression for x dot. Sorry, I forgot the sigma here. And so what you get is y dot I equal to minus sigma vi transpose L x of t. But vi transpose L from the symmetry of the matrix will be equal to lambda I vi transpose from the eigenvector equation. And so you will get in the end that y dot I will be equal to minus sigma lambda I yi. So basically what we are doing is we are diagonalizing the dynamics. So we can get an explicit solution for yit. So yit now will be, everything will be scalar. This exponential will not be anymore a matrix exponential, it's just a standard exponential. So we will have the exponential of minus sigma lambda it vi transpose x0. Now we can obtain, so our objective is still to find an expression for xt, so we can plug the expression of yi into this decomposition here. And so what we get is this. So we get this part which is related to the mode associated to the first eigenvalue, then we have the mode associated to the second eigenvalue, and so on. So with respect to the mode associated to the first eigenvalue, well, you can see that the first eigenvalue is 0, so this exponential is equal to 1. When you do the computations, you also know the associated eigenvector, which is the vector of ones. It's orthonormal, so you divide by the square root of n. When doing the products, you just get 1n transpose times x0 multiplied by 1n. Then this is the only terms that remains, because all the other terms you have lambda 2 that is a positive, that is positive, and all the others are positive. So all these modes vanish exponentially. So they all go to 0, and in the end, what you get is convergence onto the average of the initial conditions. Okay, so very nice and neat. And this is what. And so now we are at the point that we can summarize some of the facts that we have learned, and that, let's say, all the literature on consensus in the last decades has learned on consensus problems. Well, first of all, the state of the nodes never exceeds the convex hull of the initial conditions. So this never happens, okay, regardless of the topology. Then the dynamics can never be unstable. And why is that? Well, because the eigenvalues of the Laplacian are all in the right complex plane, half-right complex plane. And then if you, the dynamical matrix is minus sigma x, so this flips the eigenvalues on the other side, so you are always in the left-hand side plane. So you can only have the 0 eigenvalue, which gives you the constant mode, and then all the other modes are asymptotically vanishing. So you can never get instability. Moreover, we learn that if there is a spanning tree in the network, the consensus is attained in the network, and if the graph is weight balanced, then we also get what we like, we get average consensus. Very nice. Unfortunately, nothing of this carries out when we introduce higher order interactions. Okay, so we lose all of this. Okay, so, but first of all, why do we need higher order interactions in this context? Well, in opinion dynamics, I would say that it's quite obvious, because the process of opinion formation you have often takes place within more than two nodes. These interactions are also weighted and directed, because you might have some agents that exert a prevalent influence on the other agents. So you might want them to be influence rather than being influenced, right? And also you can weight this. So there might be some agents which are weighted more than others in a given interaction. Okay, and this is particularly relevant in control of opinion dynamics. Control, what does it mean in this context? So I teach control theory. So control theory is trying to let dynamical system behave as we like. So in opinion dynamics, we'll be trying to influence the preferred opinion in the network. So trying to do basically what this guy is doing here. Okay. So in this case, clearly the interaction must be directed, because I'm trying to influence. I don't want to be influenced. I'm just trying to influence, right? So directionality is something which is needed here. And having pairwise interactions only would mean that the leader is able to individually measure the opinion of a given node, right? Because having this edge, when we put dynamics on it, that means that I am able to measure individually the opinion of each agent. This is not often the case, so we need hypergraphs, and we need directed hypergraphs. So now the big question is, how do we define directed hypergraphs? There are several ways. As I anticipated, we will see two of them. So now here, we will focus on who is receiving the signal, on the node that is receiving the signal. For this choice, which will be useful for our purposes, so we are interested in who is being influenced in a given interaction. So we will we'll introduce this concept of target hypergraphs, in which you have the set of hyperedges. You define it, so you define an hyperedge as an ordered set in which you call the first node of this order set, you call the target node. So for instance, this will represent the node that will receive the signal, we receive the input from the others. So in this hypergraph V1, you have the hyperedge will be the hyperedge 3 to 1, because 3 will receive the node, will receive the input. Okay. So in this other hypergraph here, you will have an hyperedge 7, 4, 5. Then here is 8, 6, 5. Okay, and then you have also another hyperedge 8. No, this is just a standard edge 8, 4. So the thing is that in this way you are also allowed to associate weights to this. So you can also associate then weights to this object here, because you can associate a weight to each node in this interaction. We will see how we do it. But in principle, you can get the intuition that now we can also associate weights in these interactions. Yeah.
You are now here seeing an hyperedge like a sequence of nodes with a beginning and an end.
That's right. That's right.
So you can
Order.
consider here a situation where
Where?
frustration.
A middle?
For example,
Yeah.
1, 2, 3, 1 is forcing 2 and 3 is forcing 2 at the same time.
No. Here we are just so the role here is the only role which is defined here is the role of node 3. Node 3 is the one that is receiving the signal, and the signal is
After all the others.
no, it's the only one. So it's the only one, and the signal is a function of the state of node 1, 2, and 3. Yeah. Yeah.
So it's 1, 2, forcing 3.
Yeah. Yeah. So now the model, the simple model that we have introduced for graphs, now can be generalized in this way. So we have the interaction that in general might also, the strength of the interaction might also change with time. Then here we had the summation over all the nodes, and we had the adjacency matrix that told us which nodes are interacting and which node. Here we are summing over the set of hyperedges that targets node I. Okay, because node I, we are saying that, are you raising your hand? No. So epsilon I is the set of hyperedges that targets node I. So, and then here you have the coupling protocol. You have this inner coupling function G, which might differ from hyperedge to hyperedge. So you might have one coupling function for one hyperedge and a different one for another hyperedge. And this will be a function of the state of all the hyperedges involved in that, of all the nodes involved in that hyperedge. Okay, so here in the pairwise interaction, you only had xi and xj. Now you have all the nodes that are involved in that hyperedge, in that interaction. Okay. Now, how is this protocol built? So this protocol is built in this way. So it's the scalar product, basically, between a function alpha of the state and possibly on time, and the state of the nodes in the hyperedge. This function alpha has an important property. So it sums to 0. So if we multiply it by a vector of 1s, we get 0. Why is that important? Because this generalizes the concept of diffusion that we had for graphs. So basically, when and in particular maintains one very important property. So when we are at consensus, then the coupling disappears, right? So when xi is equal to xj in the pairwise case, that coupling term will disappear, and the same happens here. Okay. because if xi, if the x are the same, so all the xi's are the same, then this vector will be made of all identical elements. Okay. Questions? Okay, let's make a simple three-node example, also linear. Okay, so in this case, you have two target hyperedges. So here in this hyperedge, it's 2 that is targeted, so you have hyperedge 2, 3, 1, and then here it's 3 that is targeted, and you have 3, 2, 1. And then this function alpha, which in general can be state dependent, time dependent, let's pick it constant. Okay, just let's make it simple. So it's minus 1 half, and 1. So it sums to 1. So when we apply our protocol, what we get is that, well, the first equation x dot I is equal to 0. Well, makes sense. 1 is not influenced by anybody. Then x dot 2 and x dot 3 basically receive a signal which is the difference between the state of node 1 and the average state of node 2 and 3. Okay, and then they receive both the same signal. So it's like node 1 is measuring this. So this, if you want to understand what this mathematical formulation means in this case, so it means that node 1 is measuring the aggregated state of node 2 and 3. So it's measuring an average state on 2 and 3, and it's feeding back the difference between its state and this aggregated measurement that is getting. Okay, so we can formalize this case. This case, even though it's linear, simple, you cannot formalize it with graphs. So if you have standard graphs with only positive edges, and keep in mind these things with only positive edges, you can never formalize this with a graph. Okay, it's linear. Okay, so in principle, of course, you can go from higher order to pairwise interaction. But if you constrain yourself to positive interactions, you cannot do that. And interestingly, here you have a unique source, node 1, but still, you don't get consensus. Okay, here you don't reach consensus. So it seems like a similar case to this one, but it's not. Okay? Yeah.
Can you try to give just a little bit of intuition why the consensus is not happening? I can't see kind of intuitively. I see the math, but what's going on? Which ingredient is being disrupted from the other piece? What the consensus is up to?
So the ingredient is that node 1, so just an intuition, right? So the ingredient is that node 1 is not capable of individually measuring the state of node 2, and it's not able to individually measure the state of node 3. And so it can only measure, so it's a sensing problem. So it only measure the aggregated state of node 2 and 3, and so can only feed back the difference between its state and this aggregated state. So it has less resolution in its action. Yeah, that's the intuition. So these two cases are looking different. And also, if we consider the equivalent of a nearest neighbor network, but in higher order, and still everything linear, but just now the rule is different. So what does it mean nearest neighbor higher order? We say that each neighbor of a node feeds back the difference between its state and the state of its neighbors. Okay? So when you do that for n greater or equal than 5, you have that the dynamics are stable. So you lose stability. So regarding what we knew, so the first example, the consequence of the first example is that these two don't hold. Okay, so the state of the nodes goes out from the convex hull of the initial condition, can go out from the convex hull of the initial condition. Also, even though there is a spanning tree, consensus is not attained. And this example shows us that dynamics can be unstable. So you can lose stability here. For the fourth aspect, well, what does this even mean in directed hypergraph? So, so average consensus is attained when the graph is weight balanced. But what does it mean weight balanced in a directed hypergraph, in a target hypergraph that we have just defined? Okay, so we don't have even the meaning for this fourth statement. So 3 are clearly false for hypergraphs, and the fourth we don't know what does it mean. Okay, so we need to do something about it and try to get some topological conditions again, guaranteeing the achievement of balanced, average consensus, even in the presence of higher order interaction. So let's see how do we do that. So let me remind you the goal. So we have this equation. We would like to understand whether when the consensus is globally exponentially achieved, in the sense that the norm of the error, what is the error? Well, the error of the ith node is the difference between its state and the consensus value. So then you stack all the errors. So if the norm of the error converges asymptotically and exponentially to 0, you say that consensus is globally exponentially achieved. Now the x bar that we are looking for is the average of the initial condition. So we would like it to converge to the average of the initial conditions. So we need some topological condition as well. So we had the spanning tree condition for the graph. So now what are we going to have in directed hypergraph, in target hypergraphs? Well, we need to give some definitions. So first of all, in a target hypergraph, so we say that 2 nodes are related if there is a target hyperedge to which they both belong. Okay, very simple. Then we say that instead they are path related if there exists a sequence of S greater or equal than 2 nodes, with the first element of the sequence being V1 and the last being V2, so that 2 consecutive nodes in the sequence are related, so belong to the same hyperedge. Okay, so for instance, here you have that 1 and 2. So let's look to the right. So we have that 4 and 5 are related because they belong to the same hyperedge epsilon 2. And instead you have that 8 and 4 are path related because 4 and 5 belong to the same hyperedge, 5 and 6 to the same hyperedge, 6 and 8 to the same hyperedge. Okay. Notice that we don't mind directionality here in defining this related and path related. We will say overall that the target hypergraph is path related if every pair of nodes in the graph is path related. Well, in this case, you can see that this graph is not path related. Well, if we only look at this component here, well, this component is path related and this other component here is path related. So this generalized property on graph, does anyone of you have an idea of which property on graphs, which connectedness properties of graph is generalized to hypergraph here? Don't be, please speak louder, because connectedness, but which type of connectedness? Sorry? I'll make you a more specific question. Weak or strong connectedness?
English is called simple connectedness.
Sorry?
Simple connectedness in English.
Simple?
Simple, yeah.
The weak one, which one?
The weak one is called simple.
You call it simple? Okay. So weak or simple or strong connectedness? So strong connectedness is the existence of a path, of a directed path from any node to any other node. Weak connectedness is when you don't care about the direction of the arrows. So here we are not caring for that. right? So this generalizes the concept of weak connectedness for graphs to the case of target hypergraphs. So now we need to give the concept of circular class, which will be important for the balance for defining somehow the balance in the graph. So when you have a hyperedge, you can associate to it a circular class, so which is a set of hyperedges obtained by a circular shift of epsilon k. For instance, let's say that you have epsilon 1, and then you want to compute the circular class of epsilon 1. So epsilon 1 is 3 to 1. Then you make a circular shift of length 1, and you get 1, 3, 2. Make another circular shift, you get 2, 1, 3. And then that's it. If you do other shifts, you get back to epsilon 1. Okay? So this will be the circular class associated to epsilon 1. Of course, this will be identical to the circular class associated to epsilon 2 and to epsilon 3. Right? Now, we will say that a target hypergraph is circulating if it's basically close with respect to this operation of circular class. So in the sense that if you take any hyperedge in the set of hyperedges and you compute the circular class, you remain in the set of hyperedges. Okay, you don't exit the set of hyperedges. Now, you remember this alpha, this function alpha. So this function alpha, that you can see it as a function of weights, possibly time varying and possibly state dependent, but you can look at them as weights associated to the hyperedge. So this, you say that it is that the coupling protocol is circulating invariant if this function alpha is circular. What does it mean circular? It means that if you apply this function does not change for vectors obtained from a circular shift of the argument. So if you take the state of the nodes and then you change their order with a circular shift, the value of this function will not change. Okay? Now, so this is not, so this is a property that will be important for maintaining a balance in the interaction, and consider that it's not a very strong assumption, because in the pairwise case we are considering this alpha constant. Okay, so now we are not saying that they are constants. They can change. You just need to fulfill this rule. And so the entire network, we will say that it will be circulating when the protocol will be circulating invariant, and also will not change. We know that the function g can change from hyperedge to hyperedge, but within the same class, they will be the same. So if you consider two hyperedges that belongs to the same class, then the protocol is the same. Okay, so the alphas will be the same. Now, what's the powerful thing is that when you do this assumption, then even in this nonlinear higher order case, you can go from this equation to an equation that resembles very much the the dynamical equation that you get for graphs. You remember for graphs we had minus sigma Lx. Now we have something very similar. So as Charo was saying, sometimes it's comfortable to go back to something that we already knew. But of course there are some differences. So here, well, of course, sigma in general is time varying. The matrix L, we call it L, but it's not really a standard Laplacian, in the sense that it does not have the property that the diagonal elements may also be negative. The off-diagonal elements may also be positive. What you maintain is the property that the row sum is 0. So the row sum is 0. So from the Laplacian, this is what is maintained. And the zero row sum also it means that you also keep the property that 0 is an eigenvalue with associated eigenvector, the vector of ones. So this is something that you maintain. So it's still the consensus. So the consensus states are equilibria for this equation. And how do you build this matrix? Of course, we will not go into the details of that. I provided you plenty of references at the end of the talk, and also we can discuss about it in case you wish. So this matrix is obtained as the sum of the Laplacian associated to each hyperedge in the graph, and can be built, this Laplacian associated to the average can be built from this simple rule. And this is what it looks like for this example of 3 nodes, where you can see that in this example you have the epsilon 1, epsilon 2, and epsilon 3 that belong to the same circular class. So they are obtained just by shifting, and you can see that the circular shift is particularly evident graphically. You can see it graphically in this example. Okay, now that you can write it in this form, you can give some result which is, let's say, what we were looking for from the beginning. So, first of all, the network must be circulating. Okay. Then, so circulating means that all the nodes, the hyperedge is circulant. So every node. So every hyperedge, given every hyperedge, all the edges in their circular class will have to belong to the hyperedge set, okay? And then this G will be the same if epsilon k and epsilon j belong to the same circular class. Then under this assumption, if the graph is path related, the hypergraph is path related, okay? So just for the intuition, the equivalent of weak connectedness for graphs. So I can disregard the directionality of the arrows, and I can go everywhere in the network. And if the symmetric part of the, you know what is the symmetric part of a matrix? Well, if you have a matrix L which is not symmetric, its symmetric part is the matrix plus the matrix transpose divided by 2. Okay? That's the symmetric part of a matrix. So the symmetric part of the Laplacian associated to each eigenvector as precisely n minus the cardinality of the eigenvector, the cardinality of the hyperedge plus 1, 0 eigenvalues, and all the other eigenvalues are larger than a positive scalar, then you can show 2 things. First of all, the matrix L epsilon is 0 row and column sum. And so also the L, which will be the sum of all these matrices, will be 0 row and column sum. Okay? So the vector of ones, again, will be also a left eigenvector for this matrix. And, and moreover, the network will globally exponentially achieve average consensus if sigma, if the coupling gain is greater than a certain scalar. And particularly, you can also modulate with this sigma, with this lower bound, you can modulate also the exponential rate of convergence to consensus. Okay, questions? Yes. The
circularity property
yes.
is something that is related to the fact that with this formalism we have that each hyperedge influence only one node, or do you think that it can be generalized also in case of hypergraphs such that a single hyperedge can influence more than one node?
Okay, so there is an equivalent. So the answer is that if you have hyperedges in which represents cases in which more than one node is being influenced, you can make an equivalent representation in terms of hypergraphs where you only consider in terms of target hypergraphs. So there is an equivalence between these two representations. You can go from one to the other. In this representation here, what you get is that you get this circularity. This circularity makes in such a way that every node, let's say the outgoing weight and the ingoing weight for each node will be balanced. So that's the property that you are maintaining here, and it's easy to see with this formalism. If you change the formalism, then it's a little bit more obscure looking at this. So this makes this more explicit. But in principle, you can use other formalism to do the same thing. So let's conclude with an application of this. So let's consider the case in which you have consensus dynamics with homophile agents. So homophile agents are agents that interact more with like-minded individuals. So let's look at the equation here. So this will be the interaction protocol. So you will have that the interaction within the hyperedge epsilon k will be the difference between xj and x1 with for all j in that hyperedge. So the target node will be influenced by all the others, but this interaction will be, the weight of this interaction will depend on the variance of the opinions in that group. Okay, so in practice, if we belong to a group which is very like-minded, so with very similar opinion, we will get a strong interaction. If the opinions are very diverse from each other, we will tend to disregard and not interact. Okay, that's the idea. And so this is the plot of the function S, for instance. So you can see that you get, when the variance is small, you get the maximum value, and then you get a decrease in the interaction. So now let's apply to one example with a circulating target hypergraph. So you can see here that here basically you have three communities. So you have community 1, 2, and 3 with associated circular class C epsilon 1. Then you have the community 4, 5 with these two nodes, and then you have the community of nodes from 6 to 13 associated to these three classes here. And then you have the connection between the communities, which consists in this circular class of hyperedges, which connects the three communities basically. So this is the context. You have three communities connected by a circular class. In this case, it's easy so the graph is the hypernetwork is circulating, and the hypergraph is path related. So as you can see, you can go from any. So if you disregard the directionality, you can go from any node to any other node. In this case, also if you consider the directionality actually, but it doesn't matter. So and then the non-zero eigenvalues. So you have the very right amount of zero eigenvalues, and the non-zero eigenvalues associated to each circular class is given by S min, which is a parameter of the function S that weighted the interaction, times the cardinality of the graph. So we are under the conditions of the theorem, and we will see in the next slide that actually we have average consensus is attained. And what we can also, so this is what we can predict from the theory. Then simulating, we can also have an idea what is the effect of the homophily in the network, and we can see that varying the parameter Q, so higher Q means a higher homophily. You can see that what happens is that if you increase the homophily, you will favor the intercommunity interaction in the first part of the evolution. So there will be quickly a consensus between like-minded individuals in the same community, and then it will slow down a little bit the convergence of all the classes altogether. So they will still talk, but at the beginning they will talk. We don't talk much because they will be a bit far away, and then they will finally converge towards each other. Okay. So what are the take-home messages for this from this talk? Well, first of all is that even in simple problems, what we knew from on graphs, so from what happens in dynamical systems on graphs, doesn't generalize to hypergraphs. And you can have phenomena that can never appear in graphs, so such as the instability that you have seen, that you can have when you have hypergraphs. Okay, and this is something that, of course, you should never take for granted that you cannot that some results carry out for higher order interaction. Then the second message is that the type of formalism that you need depends very much on what is your scope. Okay, so maybe you don't need directed interaction, so you can completely disregard this. But maybe when you are the problem that you are tackling, you need to consider directed interactions. Then when you have to consider directed interaction, you have several options. So what we choose here is to focus on the node that is receiving the signal. We focus on that, and we build the formalism around it. But we can also make a different choice. We might be interested in the node that is sending the signal. We want to highlight that. We want to highlight its role. Okay, the node or the nodes that are sending the signal. And okay, clearly, once you choose the formalism, then you need all the topological definitions associated to that formalism, and you need to play with that. But in the end, you will be rewarded because you will find conditions that apply also for the case that is of interest for you. I will also leave you some references. These references are related to the talk, to the lecture of today. Okay, and then I will leave you also additional references tomorrow. They are grouped in depending on the applications. Well, the details on the formalism directed on target hypergraphs, you will find it here. For general results on consensus, I would address you to this book, which is quite clear in its formulation, and to this very well-cited paper from 2004. For a general introduction on complex systems and networks, this is one of the possible choices. And then for what happens with like-minded individuals, you can refer to this work here.
Thank you, Lord. So, are there any questions specific to this class? Please.
I have one question because I didn't get to understand very well the idea of path-related and circulating hypernetwork, but I have one thing to ask you about. I think it is like 2 or 3 slides before when you show the last example, right?
This one?
Yes.
Yeah.
Maybe like to clarify this idea because you asked this thing to be like path-related where you said you need a weak connection.
It's so kind of equivalent of weak connectedness for graphs, yes.
But what I'm seeing is, for example, this idea. If I'm not understanding wrong, the circulating hypernetwork in this case, when I see that network, I see that you have a strong connection between the nodes, right? Because you can have a path from any node to anyone. Like
Yeah.
you connect all these circulating. So if you ask for it to be circulating hypernetwork, is it to be like this circulating hypergraph all joined in a way that you end up always having the strongly connected condition that is stronger than the path related?
Okay, so what you might lose,
Which I want to say is, isn't it like asking if path related something that you already have when you are circulating hypernetwork or not?
no, because the thing is, so let me do it like this. This is not path related, but this is circulating. Yeah.
Good. Okay.
Yeah.
Good.
Yeah. Sure.
Other